I thought we could just begin with a short recap of yesterday's topic. Where we considered in detail the motion of a particle moving in a so-called Kepler potential, which looks like this, where k is some constant. And we were able to derive in some detail that you could actually obtain a quite compact expression for the trajectory of the particle. Which looked like that, where this parameter p was the orbit parameter, whereas epsilon was the so-called eccentricity of the orbit. Defined like this. And when we considered this expression in more detail, we saw that we could actually characterize qualitatively all the different types of trajectories that the particle could take simply by varying this epsilon parameter. And what I would like to point out here is that the fact that the orbit or the trajectory, this equation describing how the radius depends on the angle, the fact that it only depends on two parameters, so that all of these original parameters, energy, angular momentum, mass, strength, or potential, they're all combined into this eccentricity, which is a quite powerful argument because it means that it's only the combination of these original parameters in this particular way which matters. So it's only the eccentricity that matters. Because in principle, you could think that that if we start off with a problem where you have a lot of parameters, then depending on how we change these parameters individually, we can end up with a large variety of orbits. But in fact, it turns out that it's this particular combination that determines whether you get an ellipse, a hyperbole, etc. And after having analyzed this Kepler problem in some detail, we moved on to what will be the topic of today, namely scattering in a force field. And we introduced this quantity known as the differential scattering cross-section, which was basically a measure of how much of incident particles towards a force field or a potential would be scattered into a specific direction by this potential. And the potential could be either attractive or repulsive, it didn't matter. So this quantity basically tells us something about how the particles are scattered by the potential, by this source, into some angular direction. So that is what we'll consider in more detail today. And as I mentioned yesterday, it's also a very powerful tool in order to obtain information about different sources that give rise to these, to this force field, for instance. And by the way, thank you very much for your input on the reference group meeting yesterday. I have noted all the points and I've written up a small summary. And also, in addition to the summary, I've written some points concerning what I will do in response to your comments, for instance, about the problem texts being a bit scarce on some of the exercises that they could benefit from being more full. So I'll revise some of the exercises, for instance. And also I noted your comment about the writing on the blackboard, so I'll also try to make an improvement there. But I'll post it on a web page, and then you can have a look at it. Okay, so let's try to define geometrically the situation we're considering now. assume we have some scattering center here. This is sort of the origin of the potential, which gives rise to the force that is scattering the particles. And as mentioned yesterday, we're assuming that we have a force which dies out as you approach large distances. So at r goes to infinity, the force is 0. But as the incident stream of particles approaches the scattering center, they are scattered or bent from this rectilinear motion. So in this particular case, we're considering we have depicted a situation where the force is repulsive. So in this situation, if we have a beam here of incident objects or particles of some sort, we see that it's natural to define the scattering angle, theta, in the following way. It's the angle between the outgoing trajectory and the incoming trajectory. And for later purposes, I'm also defining this angle 2 psi as the remaining angle here. So 2 psi plus theta is equal to pi. Right, and I've also defined here the perihel, which we introduced yesterday, as the point on the trajectory which is closest to the center, or R minimum, if you will. So at this point, we have the perihel, Rm. So let's say we have some incoming object with mass m, a velocity v0, and to characterize these incident particles, it is useful to introduce this scattering parameter S. And so basically we're saying that depending on the distance here, we have different S's, different scattering parameters. And that gives us a way to classify sort of the incoming trajectories. And it turns out that the scattering parameter is related to the angular momentum. So the magnitude of the angular momentum is defined like this in the usual way. And since we're dealing with central forces, a potential which only depends on the radius, we know that the angular momentum is conserved. And so we only need to evaluate it at some point in order to know what it is at all points. So for instance, as r goes towards infinity, we can see that upon inspection of this figure, that the angular momentum is given simply by the momentum mv0 multiplied with s. You have r here, and you have momentum here, and so s is the component perpendicular to p. We can rewrite this a little bit more because we know that at infinite distance we only have kinetic energy. There's no potential energy. So we see that the scattering parameter s, this distance here, is in fact determined by the angular momentum and the energy if you consider fixed masses of the incoming objects. And it turns out that this scattering angle, the manner in which the incident beam of particles is deflected by the potential, is determined by this parameter s and the energy of the particles. So let's pause for a second and think if this is reasonable. So we're saying that the scattering angle should depend on s. Well, if s is small, so the particles are incoming here, for instance, it seems reasonable that they should be heavier, influenced in a heavier way by this potential energy compared to if s was large, if they were incoming here. So they would feel less of this scattering center if they were incoming far away. So let me try to draw that. Well, that's pretty. So let's say they're incoming here. They might just be slightly deflected. But if they're incoming here, it will probably look something more like this. So S will determine how or what the scattering angle will be. But in addition to this distance from the scattering center, the energy should also have an influence. For instance, if they approach slowly or in a fast way. If they have a high kinetic energy, it means they're moving fast. So they might escape this scattering center, or they spend less time under the influence of the scattering center. So they should also have a more rectilinear motion, the higher energy they have. And in contrast, if they're moving slowly, they will spend more time here and have more time to be deflected. So the scattering angle is determined by the energy or the incident velocity and S. So based on this, it seems reasonable to suggest the following. That there should be some relation between the number of particles incident between S and S plus ds, some infinitesimal increment in the scattering parameter. Should be a relation between that and the number of particles outgoing between some scattering angle and an infinitesimal increment in the scattering angle. So now the challenge is to try to express this mathematically. So if we consider the left-hand side first, the number of particles incident between S and S plus ds should be written like this. So to understand this, keep in mind that the intensity was defined as the number of incident particles per unit area per unit time. And 2 pi s ds is equal to the area of the cylindrical shell. So basically, if we have two incoming trajectories here, with ds separating them, then the area spanned by this cylindrical shell is 2 pi s ds. So this quantity here should give the number of particles incident between s and s plus ds per unit time. Now, to the right-hand side, just using the same type of argument, this will be the number of particles outgoing in this area or orbital angle between theta and theta plus d theta. Now you may wonder, why have I added this absolute value sign on ds and d theta? So the reason for this is that in some cases the derivative ds d theta may be negative, or actually often. And we can understand this based on this picture here, that if you have an incoming particle with a scattering parameter s, and then compare that to an incoming particle with a larger scattering parameter s, the scattering angle will reduce. It will become smaller. Based on this picture over here, that the farther the particles are from the scattering center, the less they will be influenced. So basically, as we increase s, we decrease theta. So the derivative is negative. And what we're after here is the number of particles incoming in a certain interval and outgoing in another interval. So it has to be a positive quantity. So you can think of this as the magnitude just of the increments in s and theta. And so this equation now gives us an explicit expression for this differential scattering cross-section as follows. So it depends on the scattering angle in the following way. So let's say we wanted to actually evaluate what this differential scattering cross-section is for some situation. Well, that entails us identifying s as a function of theta in order for us to perform this derivation. And we can obtain this by going back to our equation of motion that we also used for the Kepler problem. Namely this equation here, which, as we stated yesterday, is a combination of the conservation of energy and the conservation of angular momentum. So I just used a different symbol here for the angle characterizing the motion of the particle, because we've already spent theta as a scattering angle. So beta here is what we've called theta so far. It's the angle characterizing the motion of the particle, or the polar angle, if you will. Okay. So let's see now if we can make some good choice for these integration limits. So from this figure, from the way we define the scattering angle, we have that theta plus 2 psi here is equal to pi. Also, if we let R0 go towards infinity, it corresponds to setting the angle equal to pi. So if we just start over here, we have an angle pi characterizing the position of the particle. And similarly, if r is equal to this perihel value, the minimum value of r, it corresponds to beta being equal to pi minus psi. So basically, the motivation for writing this up is that we know the values of both r and the angle beta at 2 specific points, which we then can use here. So using these limits in the above equation, we obtain this. So now we have an explicit equation for this angle psi. It's the integral from the perihel of the trajectory to infinity of this integrand here. And why is this useful? Well, we have an explicit relation between this angle psi and the scattering angle theta. So if we're able to solve that integral and thus obtain an expression for psi, we immediately have theta, which is what we want. Now, we've seen this type of integral before. In fact, we solved it yesterday when discussing the Kepler problem. So we can rewrite this integral to that by using this relation. So note that S is to be thought of as a constant here. It's determined solely by these parameters, which are specified originally: the energy, the angular momentum, and the mass. So let's make this substitution, which we also did yesterday, precisely to be able to solve this equation. So we end up with this, and now we finally have a compact expression for the scattering angle related to S, which is what we wanted. We wanted a relation between S and theta so that we could obtain the derivative that entered the expression for the differential scattering cross-section. Like this. And as you may have noticed, we haven't even specified potential energy yet. V remains general. So now, depending on what V is, we may or may not be able to solve this integral analytically. So in general, for complicated potentials, we have to solve this numerically. But in some cases, where V is particularly well behaved, such as for the Kepler problem, one may solve this integral. And we'll have a look at a specific example when this can be solved. But before that, let me point out that this here, the periheal, is known to us, because it's a parameter that enters this expression which determines the scattering angle. So the question is, what is this upper limit? Well, we can determine it. If we take our equation of motion, which relates r to the angle of the trajectory, we obtain the following differential equation. So if you derive r of beta with respect to beta, you get this. So this is the equation we started with. And now the point that the periheal, the point of the trajectory which is closest to the center, is defined in the following way. And we can understand this by noting that this means that r as a function of the angle of the trajectory is a minimum. So it has to be the minimum, the periheal, since we have no local maximum. We only have a local minimum. So if dr d beta equals 0 defines the periheal, then it follows from this equation that um, which is equal to 1 over rm, has to satisfy this equation. Which also depends on the potential energy, but for a nice potential energy, this should be solvable. So let's now consider a specific example where the trajectory may be determined analytically, which allows us to determine the scattering angle and thus the differential cross-section. So we'll consider an example which is of historical significance, namely repulsive scattering of charged particles in the Coulomb field. This scattering of charged particles in the Coulomb field is something which was historically used in order to determine the structure of an atom. For instance, there were various models for how the structure of an atom would be by the 1930s. So one model was that the atom consists of protons with electrons sort of scattered inside some donut homogeneously, like some sort of jelly. But this type of experiment, scattering electrons towards alpha particles by Rutherford, I think, determined that the atomic sort of center was much more compact, whereas the electrons were scattered around much more loosely. So it determined, this type of experiment determined that sort of the modern model we have for the atomic structure today. So the situation at hand is that we have positively charged particles with charge Ze and Z prime e. These are incident with a mass m and velocity v0 towards these other positively charged particles with a different mass, large m. And so they have different charges, magnitude of the charges, characterized by these parameters z and z prime. So, as you might have suspected, we're going to assume that this mass here, large M, is much greater than small m. And so the center of mass is, roughly speaking, located in M. And so since M is much heavier than small m, large M is much heavier than small m, it may, to a good approximation, be approximated as being stationary through this scattering process. So we consider this as a stationary force center or potential energy upon which these particles are scattered. I think we'll take a break there.